The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Let's go ahead and get started. My name is David Sanders. I'm a professor at the University of Nevada, Reno, and I'm also chair of Subcommittee 3 of 318E. And when we started this session, or this, I should say, this code cycle, within 318E, we asked about what were some of the major initiatives that we'd like to work on during this code cycle. And one of them happened to be one-way shear. And so as part of that invitation, I talked to DJ Belarbi, who is chair of 445, the technical committee on shear and torsion, and asked him if he would be willing to assist us in this effort. And he said gladly, if I remember that conversation properly. And so we started on this idea of looking into the one-way shear equations, and as the session title kind of says, we're trying to decide whether or not it's time. When DJ gets up here, he's going to talk about a lot of the efforts and where a lot of the equations started. But we started down this road, and this is part of it. And I'd like to start out right now by just saying thank you to DJ and 445 and the people that have been working on this quite extensively, and our proposers who are going to be presenting their methods tonight. Because without their efforts and work, we would not be here tonight to have this hot topic session. But I also want to say that this is not a debate. We've seen a political season where debates can be quite entertaining. We'll use that phrase here. And the purpose of this session is not for the proposers to debate among themselves. The purpose of this session is for you to give us feedback. And when I say us, I'm talking about 445, I'm talking about the proposers, but I'm also talking about 318E. So what's going to happen at this convention is the things that you're seeing tonight are going to be coming to 318E, and we're going to begin our deliberations on the different methods and determining what is best. And when we look at the term what is best, we can imagine there could be multiple criteria that could determine what is best. And so we're looking to hear from you, the users of these shear equations, on recommendations, ideas, maybe further information that you need in order to help us determine what is best. So DJ is going to come up for a few minutes from University of Houston. Dan Kuchma from Tufts University is going to give us some background on the work that he's done. And then each of the proposal groups is going to get 8 minutes. And we're going to hold them very tightly to those 8 minutes. So I'll repeat again, when your 8 minutes is up, your 8 minutes will be up. And then the remaining 45 minutes, we have a microphone here, and the session is being recorded. And therefore, we would ask that you come up to the microphone and state your question or your comment. Remember, it's an opportunity for you to provide comments, and that way we can, again, get some feedback. With that, I will turn the podium over to DJ Belarbi.
All right, thank you, David. All right, I would like to take time here to just give a very quick overview of what we have been doing the last year and a half. But before that, I would like to thank the 445 members, the proposers that helped me to get through and help all of us to get through and get some very good models that we're going to talk about today. All right. Very brief overview. You know that the basis of the current design equation initiated back in 1963, that was at the transition from the working stress method to the ultimate strength method. And in 1971, basically, where we have the equation that we have now in the code, they might have undergone some minor changes here and there, but the major equation that we have in the code, they're as old as 1971. And then, as you know, in 2014, the 318 went through thorough reorganization of the code, and only at that time that we were asked by Dave Sander to look into maybe looking at this one-way shear design equations. If you go back to what used to be the Committee 426, in 1973 they expressed the hope that the design regulation for shear strength can be integrated, simplified, and given a physical significance so that the designer can approach unusual design problems in rational manners. As a matter of fact, what they add to it, they want that hope to be achieved within 2 decades. So we're talking about 1993. We're not there yet. Right after the print of 2014 code and before the Kansas City in 2015, the chair of 318E, David Sanders, approached me and he told me if we can look into the one-way shear design equation and with the 318 by investigating the effectiveness and safety of the current 318 one-way shear design and look also at other models that, you know, some of the models they appeared before then, the people they were debating when, if you remember the quick fix. And we start looking into maybe some thorough looking at these models and maybe we can have a groundwork so that we can come up with some design equations. So in Kansas City, we made solicitation internationally to see whoever gets a model for one-way shear design. And this is the 10th presentation that we have at the 445 meeting in Kansas City. Since then, this list of 10 proposals ended up to be 6. So we have today, that's what we'll be listening to today, 6 proposals. And these are the authors of the 6 proposals. Since then, what we did, we look at all these 6 models. As a matter of fact, we start with 7 models, and then we reduce to 6 models, or 6 methods. And we did the 3 things. One, we run the statistical analysis of the 6 proposals, as well as the 318-14 design equations through some experimental database that we have, that 445 have generated since then. And also, we look at the evaluation of all the 6 proposals of the 318 and 318 method, and we come up with the design database that we implement all these models for those design examples. And then we ask the proposer to come up with a step-by-step calculation for 4 examples using their method. In terms of the shear experimental database, these are some of the databases that 445 has generated in the last decade. We have 4 sets of databases, one for the reinforced concrete without shear reinforcement, and the number of data that we have there are 784. We have RC with shear reinforcement with 170 data point, PC without shear reinforcement 214, and PC with shear reinforcement 119. The 445D, the subcommittee that is in charge of this task, they are also looking at other databases, and these are the list of things that they've been working on. This database that we had there, those 4 ones, also they've been published in the ACI Structural Journal in September, October 2013, and ACI Structural Journal September, October 2014, and also we have a report that is online. I don't want to go through all this table here, but this gives you some taste of the analysis that we did, the statistical analysis of all the models, including the ACI 318-14. And you have here the means and the coefficient of variation. And this one, if you look at only the 318-14, the first one here, maybe I'll use this, is basically the data point. It's a data point for RC without AV, and this will give you the mean using all the 784, and this one will give you the coefficient of variation, and this will give you the number of test data they fell below 1.0 as an average. This is for the RC with shear reinforcement. This is for PC without shear reinforcement, and these are for PC with the shear reinforcement. And then on top of this, what we did, we plot all the models that we received since then. And as you see here, the dark one is the ACI 318-14, and the others, they are all the 7 models. I don't have them here by name, but these are all the various models that we received. This one gives you the V-test over V calculated here. This is the low and the high of all the data of all the models, and the star one will give you the location of where ACI fall. So you see, for example, in this case here, all the models, they are slightly below what ACI is, and this is the low and this is the high. This is for the averages, and this is for the coefficient of variation. Now, one day, David Sanders approached me, and we said, let's work on this one. He set as a goal that hopefully we can push this one for the next cold cycle 2019. And then we set here some of the dates that we have to achieve as a milestone. And if we look here from the top, by October 2018, the TAC review began after fall 2018 convention. Fall 2018 convention, we have the last convention to resolve all the negatives, and in March 2019 response to TAC comments and release to public comments, and summer 2019 a meeting to resolve the public comments, and October 2019 basically code is finalized at this time. Now, as for the 318E and 318, this has to go to 318 committee ballot after spring 2017, which is basically a year from now. From 318E to 318 at the end of the spring 2017, and from 445 to 318E, which is basically this convention. So after today's meeting, we are passing all the packages to 318E to deliberate on that one. This is the list of all the speakers that we have today. I was first here. We have Dan that's going to speak mainly on the use of the database, of the design example database and how all these models compare versus the ACI 31814. And then we're going to have the chance for all the presenters or the proposer to speak for 8 minutes to give the attribute of their model. Before I finish my talk, I would like to acknowledge all the people who participate in this effort. And the first group are the people who are basically they're either author or co-author of all the 6 models, maybe 7 models. These are all the people here. And these are the contributors to statistical analysis that was done by Professor Reinak, some of his helpers from the Europe side with Dan Kuchma and his student Sihang, and Dan, Kuchma, and Sihan, and members of 318E. They're people who contribute for the design evaluation and the design of design examples. With that, thank you, and I will turn it now to Dan Kuchma.
Thank you very much, DJ. Great to see that we have a full house. DJ was right. The room was going to be a little bit small. So anyhow, this is a picture of some tests at the University of Illinois a very long period of time ago. You can probably tell from the uniforms. And DJ was mentioning that there was some comparisons made against experimental databases. I think one of the things we recognize that what we test in laboratories don't necessarily represent what we build in the field. And there are, for a number of different reasons, and you can see the various differences. Obviously, there's a size and a cost. One of the other items that's perhaps not always appreciated is that when you look at some of the statistics from the experimental databases, it's not as if we have a uniform distribution across the various size ranges, et cetera, so we do have challenges with bias in experimental data that we have to deal with. What I'm going to talk about today is another way to go through and examine design approaches, and that is where we have a suite of a large number of different design cases, and for those design cases we compare how much shear reinforcement would be required, what does the depth of the beam need to be, etc., if there's no shear reinforcement. So there's some use in doing this, and some of the motivations are, and I think a lot of this is if you are a code of practice committee and someone is proposing a change, one question you have is, how much is this actually going to change what would be required? And one way of characterizing the amount of shear reinforcement is the percentage of vertical reinforcement times its yield strength. And it's not just new design. Very often, of course, we're using provisions for capacity rating. And one of the other things, if you were a code body, you might wonder, and if you see there's going to be some significant differences in requirements, you want to know, are these differences, where are they occurring? And are they occurring in areas where we actually think field experience is suggesting there could be improvements in performance? And so field experience becomes relevant. What I'm going to do in the next couple of slides is I want to talk about another aspect of what I think makes a design database useful, and it pertains to how we examine whether or not our provisions have some gaps and some inconsistencies and other types of problems. And I'm going to start by talking a little bit about ACI, and then I'll go on to describing the, this design database and how it was used. As many of you probably know, the VN, their nominal capacity, has a truss component and a concrete component. This is a plot of shear force on a beam versus strain measured in stirrups. The idea of course, a truss model is very old. It dates back to the very late 1800s. And that green line there shows what you would expect would be the strain in the stirrups if all the load was being taken by the truss. When tests were done at University of Illinois, Wisconsin, and other places, it was observed that, well, you start loading up and you don't see any strain until it cracks, and then it cracks, and then you see that strain increase, those pink dots, with additional loading until you get to yield. And when you looked at it that way, they said, you know what? We got this, we could say we have this 45-degree truss for the VS, and why don't we add something we call a concrete component? And it seems as if it's pretty much the diagonal cracking load, at least from a lot of tests, so let's use that. And we're, of course, familiar with our friend, VC equals 2 square root F prime C. But what ACI did was, it was sort of a, if you can think of it as K square root F prime C, we'll call it the diagonal cracking load, and we'll just always add that to the 45-degree truss. It's not quite that pure, though, and I want to talk about that for a moment. This is a plot from the current code, and on the vertical axis is the shear stress divided by the square root of F prime C, and on the horizontal axis is the level of axial stress, left compression, right tension. And so this is an expression that says, oh, you get a little bit of tension, the capacity goes down very quickly. You get some compression, the capacity goes up. But unless you want to use this other expression where you're considering compression and moment in conjunction, and then that entire shaded area is in play depending on the different results that you have. If you have pre-stressed members, you can actually, there's 3 different equations for a simplified method, and you can quite quickly hit this limit of 5 square root F prime C. There's another approach for web shear cracking, and you have this relationship, and so it starts at 3.5 root F prime C, and it goes up at this particular angle. There's also, of course, this other one which has to do with flexure shear cracking. And so what I was trying to convey in this slide is this should be something that I think we would think would be nice. It should be a line, right? What is the influence of axial stress on the contribution of concrete and shear? Shouldn't this just be a line? Should it really be this many different relationships? So what we have in ACI, I know a lot of people characterize as this effort is trying to address the safety concern for the size effect in shear, but that's not the whole story. There are other areas as well that I think a lot of people think there's opportunities for improvement. I showed this slide a few conferences ago at a 445 meeting. People said, I really like that. What it does is it talks about a lot of the areas and where there maybe are opportunities for improvement, such as, should the effect of pre-stressing an axial load be the same as just enumerated, or many of these other things that you see represented in that list as well. And what I found actually very nice in looking at the proposals that have come forth is that when I go down this list, and I think about that list relative to maybe where some of the current challenges are, I say, well, one of the nice things is there's, by and large, many fewer relationships with VC, sometimes just a couple. Pretty much all of them can treat axial load and pre-stressing the same way. They may not have the same philosophical approach, but they agree on the principle that that would be a good thing to do. A lot of them eliminate the discontinuities that we currently have in the code. Some of the proposals also use a variable angle truss model. I'm not saying that that's necessarily, is something we should do, but we've moved beyond just the 45, and a lot of them are based on a model, which is helpful. Now let me describe the design database and what we've done. What we did was we looked at simply supported members, various cross-sectional shapes, reinforced and pre-stressed. We also looked at 2-span members, and we also looked at columns. And what we did for each of these members, we designed it for many sections over the length, at 0.1 L every point over the length of the span. Here are the 20 flexural members where shear reinforcement would normally be required that we looked at. And so you see, if you gander through the list and you go to the column that is right here, these are the maximum shear stress levels we were looking at designing the beam for at the maximum section. The first 16 are reinforced concrete, and the last 4 are pre-stressed members. So this was the range, and what we did, as mentioned, at every little bit over the length, we went through and determined what the shear in the moment was. We did the full design for flexure, making sure the moment envelope was greater than the demand envelope. And then we went to all the various proposals. And for those proposals, what we did was, and this plot shows the amount of steel required as a function of the position over the length, and green is ACI, and I'm not showing the names of the others, but this is sort of the range of different results that we received from what would be suitable levels. So it is still quite a range that's out there in terms of ideas. We also looked at slabs, and we looked at slabs where you would not have shear reinforcement. And for those, what we did was we said, let's look at what depth of slab would be required for different levels of superimposed load. And there's ACIs in green, and as you notice, pretty much all the proposals are saying much thicker. And that's because this is the specific safety issue associated with the size effect in shear. So, thanks.
Thank you. Our next speaker is Tony Cladera from University of Balearic Islands.
Thank you very much. I'm going to present the work that we have been doing in Spain in the Technical University of Catalonia by Professor Antoni Marí and Jesús Bairan, and by myself in Mallorca. We have presented a proposal that it's a code proposal based on a mechanical model that we call the Multiaxial Model that takes into account the influence of the compression curve, transfer action, the tensile stresses across the crack, the Dowell effect, and the steel stirrups. When we derived the original mechanical model, we took into account equilibrium, kinematics, and for sure a failure criterion that was the Kapfer's failure envelope. After that, okay, we had one equation for each member, for each action. What we have done is to compact all the expressions, so to put the residual tensile stresses inside the compression curve action and the Dowell effect inside the stirrup actions. So this way we have a quite compact expression, you will see later, and you will see that it's safe and economic. We will compare with the databases. It's accurate, and I think that that's very important for evaluation of existing structures. It's easy to use. We have one main equation for beams for BC, and then one additional check for slabs. And it's also adapted to non-slender beams, shear, steel fiber reinforced concrete, beams reinforced with FRP, fatigue, punching shear, and other things. Here you have the basic equation. We have a concrete contribution plus a steel contribution. This is the concrete contribution. This same compact formulation is valid for reinforced and pre-stressed concrete beams with and without stirrups, with or without axial load, compression or tensile load, and with rectangular T or I cross section. And the key parameter is going to be the neutral axis depth or the relative neutral axis depth. Then this is the steel contribution, and we have an additional check that is the strength of the strut. Here, this equation comes from plasticity. This is the equation that we are using in Europe in the Eurocode. And okay, this equation maybe it's a little bit more complex, but if we take average value of the different parameters, we go to something that is from 0.24 to 0.27, and this is the expression given by our Canadian colleagues, and it's quite similar, but of course it could be simplified, that's for sure. And the key parameter is the neutral axis depth. You can calculate, you all know, for reinforced concrete beam, but we propose just to use a very linear equation, very easy to use. And then how are we taking into account the pre-stress actions or the tensile loads, where just we change C over D. For example, for pre-stress concrete beams, we made an interpolation between the reinforced concrete solution and D, taking into account the stresses, the compression stresses here in the web and the tensile strength of the concrete. Then another key aspect is that we take into account the compression flanges by means of this effective width for shear strength. This value is very easy to obtain when C is lower than 8. It's just the width of the web and 2 times 8 here. And this allows to take into account the compression flange effect. And then we have also a combined, what we call a combined size and slenderness effect. We have improved the size effect since the last meeting, and in fact, we have adopted the ACI 446 coefficient here, or Professor Bazan size effect, as we all know that. We shared some emails with him, and we saw that, in fact, the models are quite similar from a conceptual point of view, and we also take into account the slenderness. For some members, for example, members with a small depth and not heavily reinforcing bending, some one-way slabs, we saw that our initial assumption that we only consider the concrete core contribution and we put this inside was not really correct, because for these kind of elements, slabs, let's say a slab with a small depth, their residual tensile stresses are very important, and we think that this case illustrates the benefits of having a sound background mechanical model, because we went back to the model and we see that if we, for this kind of elements, we have a check of a minimum shear strength, then this comes from the residual tensile stresses, this is the compression curve, and for this element we have much better results like this. Well, here you have the results of the evaluation. Thanks to the work by Professor Kuchma, you see that the proposal has very constant mean value of the experimental strength. This is the VTs over VPRET for our proposal, always lower than ACI, and also the coefficient of variation is very steady. It's a little bit different for precast concrete beams without stirrups, because here we have two different cracking possibilities, and because that's why it changed a little bit for our proposals. At this point, I would like to share with you one thought of Dr. Golder. He wrote down this in the first issue of Geotechnic, and he was talking about earth pressure, but maybe he was thinking on shear strength, I think, because he was saying that for the engineer, there are many possible answers to natural problem, all of which are compromises between the truth and time. His answer must be sufficient for a given purpose, and for this reason, an engineer must make assumptions. I think this is very important because we are going to see different models. I think they come from different assumptions. They are not more correct or less correct. They must work for a given purpose. And I think that we have been always thinking in designing of new structures and also the evaluation of existing structures. For us, it's very important to think in evaluation, because 25% more of stirrups, for example, is not a problem when you are designing a new structures, but it can be a problem when you have to strengthen a structure. In Europe, for example, we are proposing to combine our model with a plasticity model, because plasticity models without concrete contribution works very well for beams heavily reinforced on shear, but they perform poorly for beams with a low amount of stirrups. This is the plasticity model, the red dots, the current model in the Eurocode. The blue dots are old models. So, for example, in Europe, we are proposing to combine both. Just to conclude, I think that the proposed model has very easy to use equations with a sound mechanical background. One main equation for BC, valid for reinforced concrete and precise concrete members, with and without transverse reinforcement, with I, T, or rectangular cross-section. It takes into account the beneficial influence of compression flanges, and the mechanical background allows its extension to different cases. We have worked even for punching shear with this model, and the predictions are accurate, and we think this is important for evaluation of existing structures. Thank you very much.
Thank you, Tony.